Saxon Advanced Mathematics, Lesson 10. Greetings, my students. We have survived the first round of geometric proofs. Hopefully that homework went okay for you. And in the next lesson, which is where we're at today, we're going to do something completely different. So you get to rest the part of your brain that is currently under construction for proofs, and we're just going to do some good old-fashioned algebra. It's all review. It should all be quite familiar. It's a fairly long lesson, so buckle in, but I'm hoping that you will find it not horribly challenging. Equation of a line. You know the score. It's y equals mx plus b. This is called the slope-intercept form of the equation, the way this is written. There are other ways we can write the equation of a line. We're going to talk about those in later lessons. Remember that m is the slope. It defines how much tip there is to the line, whether it's going uphill or downhill. We always write the slope as a fraction. If it's a positive slope, we think of it as the rise over the run. The rise we measure by going up, and the run we measure from going across. Up and across from what? It's up and across from the y-intercept. We'll get to that in a minute. If the slope is a negative number, then it's the sink over the run, because we start measuring down instead of up, but always to the right. If we went down and to the left, then we would be doing the very same thing as here. So we only change one of those when we go to a negative. All right? B is what we call the y-intercept. It's the place where our line crosses the y line of the axis. When we're graphing, we always graph this first, and then we use the slope as a treasure map. Right? So we find our y-intercept, we put a big fat dot there, then we go up and over or down and over according to the instructions of the slope to find our second point, and then we plot that little puppy, right? Now, sometimes we're given 2 points and we're asked to find the equation of a line. When we do that, we have another formula that we use. It looks like this. This is called the slope formula. And that's kind of confusing because this is slope-intercept and this is slope formula. Their names are really similar. But just remember that this is what we do when we're trying to find the slope and we've been given 2 points. We solve it like that. We use this to find m, the slope, to find m, and then to find b, I'm writing, then I'll talk. You know this, I'm just saying it in words. To find b, we would first calculate m and use that and 1 pair of points, right? Because in these we're given 2 pairs of points. We'd plug it into our typical y equals mx plus b and then solve for b in order to get b. And that's how we can find the whole equation, right? Let's Let's try a problem doing this, and then I'm going to talk a little bit about horizontal and vertical lines. The freak children of this topic. All right, example 10.1. Find the slope-intercept form of the equation of the line that passes through the points -3, 2, and 4, -3. Okay, as soon as we see these points, what triggers in my brain is I think, oh, there's the points. x1, y1, x2, y2. Naming them like that helps me remember, oh, I'm gonna need this puppy, aren't I? That's how my brain starts to put this all together. I also know that I'm aiming for this, right? This is my goal, because John told us to find the slope-intercept form of this equation. Okay, so that's my goal. This is the formula I'm going to need to get the m, right? This is the two-step part. For first, I find m. This is just like what I wrote on the last page. Okay, so now I see there's minus signs in my formula and there's minus signs in my values. I'm using buckets. Sorry. Sorry, not sorry. Okay, y2 is -3. y1 is +2. x2 is +4. x1 is -3. That part, slow down and be careful. It's so easy to make dumb mistakes in that, and that's just so annoying. Okay, -3 -2 is -5. 4 plus 3 is 7. So my slope is -5/7. Okay, that's cool. That's good to know. I'm just going to write it again because it's kind of the m and the value are kind of separated from each other. I want them to be close. All right, now I need to find b. So that's what this work is going to do for me. And I remember that to do that, I'm going to use this value for m and one or other of the pairs of points. It doesn't matter which, it'll work either way. But I'm going to plug those in for the y and the m and the x, and that will allow me to solve for b. I'll use this first pair of points. What the heck, it doesn't really matter. And so I'll say I'm using this format, y2 equals m -5/7 times x, which is -3. Make sure you take the x and the y from the same pair or you'll screw everything up, plus b. Cool? All right, so I can see I want to isolate him. Sorry, I had to yawn. Then I have to get rid of these numbers. I have to push them that way. But let's simplify first. This becomes 15/7. So I want to subtract 15/7 from this side. To get it to cancel, I'll do 15/7 here. Ooh, that's crooked. That bothers me. That's going to all be gone. This I better rewrite as a fraction with a 7 on the bottom. So this is going to be 14/7. 14/7 minus 15/7 equals -1/7 equals b. Oh my gosh, it's so cute. So now I'm ready to take my two answers and plug them in. Y equals -5/7x minus 1/7. As much as I hate it, the x is often written as a floaty between the slope or after the slope, right? Instead of making it part of the numerator, which is normally what I would like. Tradition is to float it. This should be floaty too. It's kind of up there. So whatever. I don't like floaties, but I'll deal with it. All right, so that's the typical type of problem we use for finding the equation of a line. Before we go on to the next example, which is similar, let me just say a few words about horizontal and vertical lines, the freak children. A horizontal line has a slope of 0. Does that make sense? Here's our grid. I'll make it in a different color. Right, here's our line. That has a slope of 0. And so the formula is just going to be right, because this is at positive 2, let's say, right? So the slope is 0, so this whole term can drop out, and we can just say y equals 2. Okay, so a horizontal line is going to have an equation that looks like this. The slope is 0, so it drops out that term, and it's just y equals. And that tells us go to 2 on the y-axis and draw a horizontal line. Okay? A vertical line has a slope that is undefined. Whoa. Whoa, that is something different, isn't it? So we don't have, whoops, we don't have what's considered a normal slope at all. We have something that looks like that, right? It doesn't touch the y-axis. So no wonder the slope is undefined. It's weird. It's just totally weird, right? So what we say for this is that, okay, we do see that it crosses the x-axis. So for this, we just say x equals 2. It crosses at 2 on the x-axis, and that's it. That is how we write the equation of a vertical line. So, they're both weirdos, the horizontal and the vertical line, but I consider the horizontal line to be a lesser weirdo because at least he has a y. His x term just drops out though because the slope is 0, and so it's just the y-intercept only at the end, right? Horizontal line is weird, but the vertical line is even weirder because it doesn't even say y equals, right? It just has an x. So I don't necessarily expect you to memorize this per se, but I expect you to be able to logic out how to find the equations of these lines when you draw a picture and think about what's happening with them, okay? So slope equals 0, slope equals undefined. Y, the equation is y equals a plane number. This one is x equals a plane number. Okay, so there's a few words about those. We don't encounter these very often in our work. All right, back to normalcy, if that's what you can call it. Example 10.2. This is a fun variation on the first example we did. Find the equation of a line that passes through the point -2, 5, and is perpendicular, remember that's the sign for perpendicular, to the line 3y plus 4x equals 2. Now what is that rule about lines that are perpendicular? I'll tell you. Dun, 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 dun. If two lines are perpendicular, then their slopes are negative reciprocals of one another. So if we can find the slope of the quote-unquote other line, then we can easily find our own slope and go from there. So we're not going to need to use that slope formula, the m equals y2 minus y1 over x2 minus x1, we don't need to use that. We have another way to find the slope, which is a good thing because we only have 1 point, so we couldn't use that anyway. But now we've got another thing. What we have to do is we have, this is what I call the other line. It's not our line, it's the other line. We have to find the slope of the other line. Well, okay, that shouldn't be too hard, but we look at this and go, shoot, it's not in the right format. It's not equals in y equals mx plus b. So we have to rearrange it first. 3y plus 4x equals 2. We're going to kick the 4x over. 3y equals negative 4x plus 2, and then we'll divide by 3. And we get y equals minus 4/3 x plus 2/3. That's disgusting, but we don't mind. We want the negative reciprocal of this. So we can say that our slope equals positive 3/4. Oh, that's so nice to know, isn't it? Such an easy way to find it. Now all we do, so this is our first step, and then our second step, which I'll complete on the next page, is we use our slope and the pair of points to find b. And the way, I'll set it up here and then I'll solve it on the other page. So we're using y equals mx plus b. I'll write that again. We're always using that dude, aren't we? Okay, so y is 5 equals m, we use our m, 3/4. X is minus 2 plus b. Okay, let me write it here too. Y equals mx plus b. We use these points as our x and our y, right? Minus 2 for x, 5 for y. Our slope, we found right here, it's positive 3/4, and b is what we're trying to find. So now we just solve this and we'll have our b. So I'm going to copy it. And we'll solve it. I'll simplify this first. This is minus 6/4. So we'll add 6/4 to both sides, right? I'll change this so it's a fraction with a 4 on the bottom. That would be 20/4. And this all cancels. I add those. 26/4 equals b. And I see these are both even, so I can cut them down. 13/2 is the reduced form of that. And so now I'm ready to write my final answer. The equation of the line that meets the qualifications that were given to us is y equals 3/4 x plus 13/2. And that's the right answer. Right? So the trick of this one is remembering that perpendicular lines have slopes that are negative reciprocals of one another. And that's how I was able to take that other line and squeeze it until we got our line. Yay! Okay, there's one more. All right, I'll show you in the book because it's a picture. Find the equation of lines A and B. All right, so I look at these and I go, okay, well, B, I'm gonna have to find some points. I've got some calculating to do there. Let's look at A first. A is a horizontal line. Okay, I remember that horizontal lines are the lesser freak children. So it has a slope of 0, but it does have a nice y-intercept. The y-intercept is minus 2, so I know that the equation of this line is this. Here, let me write it down. It's a horizontal line, so I know that y equals 0x, right, because the slope is 0, and then the y-intercept is minus 2. This drops out, so I can just say y equals minus 2. That's the equation of that line in the picture. Cool, right? I'm just looking to check my answer. Where is it? Yes, that's right. Okay, now we have to do the second one. And I'll be honest with you, this annoys me because we have to like count the slope from the picture. I don't like doing this. We have to find a place where, oh, here's what I would want to do. John does it differently, but this is how I would like to do this problem. Do you see how this line begins at a perfect corner of John's graph paper and ends at a perfect corner? That means we can use those two places. Excuse me, I'm sorry. I guess I'm boring myself. No, no one could think this is boring. We can use these two locations as points, copy them, calculate the m, calculate the b. All right, so we can use our slope formula. So I'm going to call this point, let's see, it's minus 6, minus 5. So that's one of my points. And at the top, there was also another nice clean point. That would be at minus 1, 6. There might have been some other places along this line where the points went right through the corner of the graph paper, but I don't like to guess. And that's my biggest annoyance with these kind of problems where we're looking at John's picture and trying to pull the points out. It's hard to tell and it's just annoying to try and do that. So I'm pretty happy with these 2 points. I'm going to use them with the slope formula to find m. Let's see, I'll do x1, y1, x2, y2. I'll write the formula out again so you have it in front of you in case you don't remember it. I'm going to use buckets because I've got minus signs in the formula and minus signs in the values. Okay, 6 minus 5 minus 1 minus 6. Right, now I'm going to be careful to simplify, remembering that I'm adding and not subtracting or multiplying. That becomes a plus, so I get 11 over minus 1 plus 6. Aha! That is my m. And it's positive, right? These both turned out to be positive numbers. Beautiful. Okay, now I'm ready to find my b. I'm going to need to use one of the points. Let's use this one. And remember, I'm setting it up as y equals mx plus b. I'll have a value for x and y, and I've got a value for m, and that will help me solve for b. So 6 equals 11 over 5 times minus 1 plus b. Make sense? This then becomes, I can just do that to simplify that. And so I'm going to add 11 over 5 to both sides. That will cancel all that out. I'll have b by itself. Over here, I better make this a little gnat flying in the camera. I'm so close to the bottom. I'm going to scooch up a little. I'm going to fix this 6 so it has a denominator of 5. So I can add this, and this becomes 41 over 5. That's weird, right? But it's right. And so I use these 2 pieces of information to write y equals 11 over 5x plus 41 over 5. And John agrees. Okay, so in this one, we weren't told what the points were. We had to look at the picture, the graph, and find the points for ourselves. So that's what was the change in this one. Okay, there's our nice review of equations of a line. Let's move on and talk about rational denominators. John does a bunch of theoretical talk that I'm going to skip as a preamble and just weave into our problem. Okay, there's our problem. We're dividing this binomial by that binomial, right? We've written it as a fraction, but it also means division, right? It's also what we call a ratio, right? A fraction is a ratio. It's another way of saying it. Now, here's the thing about us mathematicians, which I include you as part of. This is an irrational number because it has square root of 3. That means it has infinite, non-repeating decimals. I know that square root of 3 is going to introduce that. I've got a subtraction here, but I know that as soon as I include that as part of my problem, I've created huge drama in my denominator. And as a mathematician, I don't want that. I don't want to deal with that. I don't mind if it's in the numerator as much, but I don't want it in my denominator because then it's just a giant mess. So what we want to do is we want to rationalize the denominator. We want to turn this into a number that is a rational number. It might have infinite digits, but at least they repeat. And we'll talk later about that. Later in the year, we'll talk about how that's kind of a cool thing. But these irrational numbers in the denominator, no, they skeeze me out. I don't want them. So we have to get rid of them. How do we get rid of them when we have a binomial? We use what's called the conjugate. We take the same two numbers and we change the sign in between them. This is called the conjugate. The only thing that changes is the sign in between them. Not the sign in front of the first one, but the sign in between them. Magical things happen when you multiply a binomial by its conjugate, and we'll do that in just a minute and you'll remember. However, if we do it to the bottom, we have to do it to the top. Okay, so we're multiplying that. Now, we're going to do this actual multiplication for the bottom first to make sure that the conjugate really does its magic. Because they're both binomials, we have to do the dance, the long drawn out thing, right? 2 minus 3 square root of 3 times 2 plus 3 square root of 3. All right, that's what we're multiplying. I write it in this form. Now I multiply. 2 times 2, 4. This becomes minus, remember it's pig times pig, wolf times wolf. 2 times 3 is 6, square root of 3. She's done, over to her. Now again, wolf times wolf plus 6 square root of 3. Oh, that's interesting, that's the magic. Then we multiply this. We get 3 times 3, and then these two go together to make one more 3, don't they? So it'll be 3 times 3 times 3. We know that's 27. And the sign will be minus. Makes sense? Because there's a plus and a minus. So that's minus 3 times 3 times one more 3. And that's 27. So this is doing exactly what we hoped it would do. The radicals are canceling out, and we're left with an integer. Now, that's a disgusting integer, negative 23. It's a prime number. It's negative, but it's fine. That makes us happy. Now we're going to multiply the top, and by bottom and top, I mean denominator and numerator, but those are cumbersome words. So now we're going to multiply these two. 4 plus the square root of 3 times 2 plus 3 square root of 3. We choose the conjugate of this. This just has to match, and these numbers just have to suck it up and deal. They might not be pretty, but that's what they need to be. So now we multiply. 2 times 4 is 8, plus 2 square root of 3, then we go this way, plus 12 square root of 3, and then this is going to be positive 3 times another 3. So this is going to be 9. Make sense? So we add these together. 17 plus 14 square root of 3, and now we put them together. This is the bottom, this is the top. 17 plus 14, square root of 3 over minus 23. Now, this is correct. It's just fine, but it looks a little weird because we don't usually have a negative in our denominator either. We're fine with negatives up here, but we'd prefer to see this without a negative in it. So I'm gonna multiply top and bottom by -1, right? This is fine. We're just gonna flip the signs on everything. I'm careful because this is a binomial. I'm gonna have to multiply both terms by -1. So what this will equal is -17 minus 14 square root of 3 over positive 23. This is the cutest version of our answer. If you gave me this on a test, I would hand the paper back to you and ask you to revisit the minus signs. And by that, I would be saying, yo, remember, you're not supposed to have a minus sign down here. Bump it up by multiplying top and bottom by -1. This is what I would be wanting to see, okay? So I would give you another chance to do that. All right, let's do one more problem with these. And then we have a third topic. I see it is a long lesson. After this problem, you can take a break if you want, but let's get through this one. 10.5, simplify. Okay, go ahead and finish writing. As you write this, you may be noticing a couple weird things. These can be simplified, right? Because for every 2 i's, we can transfer that to a -1, which makes things a lot simpler. So this is a good piece of information that we can use to simplify. The other thing that's bothering me is that when we have complex numbers, which we do because we clearly have i's in this, we want to format them always like this. We want to have the real numbers first and then the imaginary numbers second. This is backwards to me. I don't like that, okay? So we will simplify the top, make sure it's in this format, then we'll rearrange the bottom so it's also in that format. So let's go here. This, I can take out 2 of those i's. That will leave us with 1. 2 of them give me a -1. That changes the sign here. I circle it to show that I've changed the sign. Here, we can take out 4 i's, right? So we'll be multiplying, it'll be -1, there's 2 of the i's, times -1, there's 2 more of the i's, plus 1 more left. These two go together to make a +1, so this sign stays exactly the same, but this goes away completely. It's just a 1, right? So there's the plain 1. Okay, I like it. So now we can write this as 2 plus I plus 2I. Oh, then those can go together and we get 2 plus 3I over, and then we can just rearrange that, 4 minus 2I. Oh, this looks much better than that, doesn't it? We've cleaned it all up and got it into a much more conventional shape. I don't know about you, but I'm feeling a lot better. Now, once again, we want to rationalize our denominator. We don't want an imaginary number down here if we can help it. So again, we want to rationalize. All right, the way that we do that is the same tool. We use the conjugate, 4 plus 2I. We leave them in the same order. Everything stays the same except for the sign in the middle. So that, once again, is our conjugate, which is just a great tool for getting rid of drama in a complicated denominator. That's why we choose it, is because it's the conjugate of that. We have to use the same thing on the top and bottom rule, right? So once again, we multiply by the bottom first. We do that multiplication first to make sure the conjugate is doing its job. Plus, it's just super fun. 4 minus 2i times 4 plus 2i. We do the dance. 4 times 4, 16. Minus 8i. Then here comes the other one, plus 8i. Now we're multiplying this. This is going to be minus 4. But then here's an I squared, so that's a minus 1, so it's going to be plus 4. Does that make sense? Let me write it again. It's minus 4i squared, which is minus 4 times minus 1, which is plus 4. So I write plus 4 over here. Feel free to show your thinking process here. Write down whatever it's helpful for you to write down. If you can carry it all in your head, I'm fine with that. If you want to just make some notes to yourself, do it however you want. 20, and that all cancels. So now we've got a really nice rational denominator. This is the bottom, right? So much better. Love it. So now we've rationalized it. So now we want to fix the top as well. It's not going to make, the imaginary number is not going to go away though, because we're not using the conjugate of the top. We're using the conjugate of the bottom. So the top's going to be a little messier, but that's okay. 2 plus 3i, 4 plus 2i. 8 plus 12i plus 4i. Okay, now this, let's see, 3 times 2 is 6. Then the I squared, that becomes 6 times negative 1. That becomes negative 6. So I'll write that over there by the 8. 2 plus 16i is what we've got. I'm going to write that here. 2 plus 16i over 20. Right? And that equals, let's see, we can factor a 2. Here, let me write it on the next page because we've got a lot of steps to simplify this. It's 2 plus 16i over 20. Okay, so the first thing I notice is everything's even numbers. So we can factor a 2 out of the top. Right? And then we can cancel. This becomes a 1 and this becomes a 10. Right? We can't, that's the proper way to show that canceling. We could kind of do this step in our head and get to this answer, but you can't cancel directly here. You have to factor first. Okay, so now we have 1 plus 8i over 10. But remember, the proper format for a complex number is to have separation between the two. So that means we want to make this 1 over 10 plus 8 10i. We want separation between the real and the imaginary components, right? So that's what I'm doing here is I'm saying, I don't want you in the same fraction. You have to be separate. I push them apart, real and imaginary, but now I see I can reduce the imaginary part one more time. So my final answer is 1 over 10 real number plus 4 over 5i for the imaginary component. Oh, I'm doing the wrong thing. This should be a box. I've gone cloud crazy today. That's the right answer. Yay. All right, that's 2 of our 3 topics. We still have to do one completing the square problem. If you are in need of a mental break, pause me now, come back soon, and we'll do the last section. Okay, I'm ready to go on. Completing the square. I just had Ella Cochran here and we reviewed this. So my brain is fully up to maximum G's on this topic. Remember that when we have a quadratic equation that looks something like this, right? That's the standard form of a quadratic equation. There are 3 ways to solve. The first way is just by looking at it. We call it factoring by inspection. And it's where we set up the 2 brackets and we say, okay, we're parentheses, and we're looking for numbers that multiply to C and add to B, and then we write the X here, and then we fill in the blank, right, with the pluses and minuses as we need them. That's one way. That works if the answers to this, if the values for X are integers, just simple, clean numbers, plus or minus. It works fine. However, we often have messy answers with fractions or radicals or even imaginary numbers, and we can't just pull those out of our brain by looking at it. So we need another method that allows us to find all the crazy solutions. And that's where completing the square comes in. Now, the problem with completing the square is that there are so many steps to it. We'll review them in just a minute. It's kind of a headache, unless you're a psycho like me who loves it. But there's so many steps, and mathematicians back in, I think the 1700s was when they did this. They thought, there were several people who came to this answer, I think on their own. They said, what if we found a shortcut? What if we found a formula using the A's and the B's and the C's that would allow you to jump right to the answer without having to do all these ridiculous steps? So that's what they did. And they found what's called the quadratic formula. And you know it, it's x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. This is the shortcut that allows you to forego all the steps of completing the square and just jump to the answer. Of course, it takes quite a few steps to simplify all of this, but that's a different drama, right? So what we're doing in this part of the lesson is we're reviewing this completing the square process, solving a quadratic equation the long way, using the step-by-step approach, okay? So let us go through it. And there's just one of these, and then we're done with this lesson. It's a long one, right? Okay. They give us a quadratic equation. And tell us to solve it by completing the square. All right, the first thing we notice is drama in the way this is arranged. It does not look cute like this. So the first step is to put it in standard form. Okay, so we want the 3x squared first, and then we'll have the x term, and then we need to swim this back across so it becomes a plus 5. And we set it equal to 0. Just like this. This is standard form. Okay, make sure you have this in your notes, and make sure you're copying these steps down. Of course, you're writing down everything I say. I know that. But make sure that you keep this close to the surface because it is a lot to remember. All right, the second step is we're going to kick C to the curb. Now, there's a reason that I don't just say move it to the other side, because later we're going to use a variation on completing the square, and we're going to have to find another way to move 5 off to the side, but we're not going to move him to the other side of the equal sign. So that's why I don't say swim C to the other side. It's because later I would have to eat my words and change that. So I'm saying kick him to the curb. In this context, we can see, oh, that means he goes over. 3x squared minus x equals minus 5. Now, notice how I left the gap there? Fill in the gap with the magic number. We have to calculate the magic number. The magic number, we take the b value, we divide it by 2, and we square it. We also draw an arrow right there because we're gonna need that number inside the parentheses for something later on. So I draw the arrow to remind myself, oh yeah, that's helpful. In this case, our b value is a -1, right? So in this case, it's -1/2 squared. That's 1/4. Now we have to add it to both sides though, don't we? I did something wrong. I did something wrong. We needed to divide away that lead coefficient. Okay? So this is wrong. And that would be there. Okay? My bad. When we are using the third strategy, we can leave a coefficient there, but for completing the square, we can't. All right? So that means that when I go to calculate my magic number, I'm not using -1. I'm using a b of -1/3. And so now, instead of dividing by 2, I'm going to multiply by 1/2. Does that make sense? Same difference, right? So, pardon me for being confusing, but you know what? I make mistakes too. The trick is to find them. The reason I thought to do that now is because I was thinking this problem seems like it's way too easy for where you guys are at. And then I looked back at the problem and realized I had skipped that step. Okay, so this is what we should have done way back here. When I was putting it in standard form, I should have gotten that x by itself. So now I'm going to recalculate my magic number. It's right here. I'll draw the arrow to that. This is -1/6, and when I square it, I'll get +1/36. Yeah, that looks more like what John would have for us. Okay? So let me write it again just so it doesn't look as confusing. X squared minus x/3 plus 1/36 equals -5/3 plus 1/36. Lord have mercy, right? Now, what we've done here is we have created a perfect square. This number that we drew the arrow to, is what goes inside of these parentheses. That's why I draw the arrow to it, because when I get to this stage of writing this as a perfect square, that's the number that goes inside the parentheses. Okay, just like up here, this is the number that goes in here, and we can test it the same way. These two numbers should multiply to this. Yes, they do, right? +136, and they should add to this. -1/6 plus -1/6 is -2/6, and that reduces to -1/3, and that's what we have right there. So this works out. I can also write this like so, right? This is the same as this. This part I like to write to help my students see what we're doing to collapse this expression down to this. It's kind of an intermediate step that helps your brain follow along. When you get the hang of it, you can go from here directly to here. On the other side, I've just got two innocent little fractions, but this one needs its denominator fixed, so he looks like that. So I need to multiply by 12/12. That will make this -60, right? And that'll be 36. -60 plus 1 equals -59/36. Well, that's fairly outlandish, isn't it? All right, this is what I've got. I'm gonna flip to the top of the next page. Come along. Come along, why don't you, and find out what I do next. Okay, so we have x minus 1 over 6 quantity squared equals minus 59 over 36. That's where we were at the end of last page. Now, I want to get this square to go away. So I'm going to square root both sides. All right, that makes things look really good over here. But over here, I've got drama. First of all, because I'm taking the square root, I know I've got a plus minus situation. Let's just leave this negative square root of 59, but I can see I had a perfect square on the bottom, so I can bring that 6 out. Right? That's a pair of 6 pigs, so I'm bringing them out. There's no longer a square root in the denominator. This has got an imaginary number because this is an even numbered root with a minus sign. So I can rewrite this as square root of 59i, like so. Okay? The I does not go inside the pig house. All right, so that's all cleaned up. It's plus or minus though. Let me write that again. Now I want to add 1/6 to both sides. X equals 1/6 plus or minus the square root of 59 over 6i. That's our final answer. Cool, right? And this has got that nice separation that we like for complex numbers, right? Even though the denominators match, we don't want to put them together. We like their separateness because we want to keep the real and the imaginary numbers very much clearly identified whenever we have a complex number like this. This is our right answer, okay? And I hope I didn't confuse you too much back here. When you're putting it in standard form, make sure you have a 1 coefficient in front of your x squared terms. Divide away whatever you need to get that by itself. That's what I forgot to do. Okay, yay, lesson 10 is done. The Algebra 1 kids today remembered in their lesson, they were reviewing the fact that you cannot divide by 0. It explodes the kingdom and causes all kinds of problems. So I dug out a video for them to watch, and the Seahawks released a new compilation of kingdom implosions because this, I believe it's this year, is the 20th anniversary of the kingdom coming down. I think it was 2001. But anyway, they put together a nice compilation of the kingdom because Lumen Field sits in the exact spot where the kingdom used to be. It might be the parking lot for Lumen Field, but that plot of land is exactly where the kingdom was. So I'm going to put that link in your description just for fun, because who doesn't like watching the kingdom implode? So check it out when you have a minute. All right, thank you, goodbye.